Welcome everyone. This is the fourth and last session of the training on high performance analytics and visualization, organized in the context of CBase project by CMCC and DKIZ. In case you missed yesterday's session, my name is Donatello Elia. I'm a junior scientist at the Advanced Computing Division at CMCC Foundation. And I'll be presenting during this session with my colleague Fabrizio Antonio, also from the Advanced Computing Division at CMCC. Yesterday we saw some key aspects of the Ophidia framework and the use of the Ophidia Python module. Well, today we're going to focus on data analytics workflows, also with the Ophidia framework. Okay, so as mentioned in the also yesterday, scientific workflows are very important since they allow to code the multiple steps of an analysis into a single document, and this can be used to run the analysis in an automated way. So in this slide, I'm going to introduce some of the challenges and the key concepts of the workflows. So complex analysis, as I said, can involve multiple datasets and hundreds or even thousands of analytical tasks. Scientists have been mainly relying on their own custom code and scripts for running this analysis. But as the complexity and the scale of the analysis grows, this approach can lead to difficulties or inefficiencies in the execution, which can negatively impact on the research productivity. In this respect, end-to-end workflow solutions can be of great benefit for larger scale experiments. In this case, in fact, the use of more advanced programming models, which are able also to handle task concurrency and to automatically optimize the execution, thanks to a higher level abstraction that hides the lower level aspect, could speed up the overall analysis. This could be very effective, especially as the analysis grows in insights. Parallelism can be handled at different levels. So, for example, this can be handled at the level of a single task by parallelizing the execution of an analytic operator, as we saw yesterday, but also at the overall workflow level, in which multiple tasks can be executed concurrently if there are no dependencies among each other. So, workflow management system, which are the components responsible for handling the workflow scheduling, can automatically orchestrate the workflow task and can also provide some nice additional features which allow, for example, the optimization of the execution in basically in an automated way, as well as fault and error management, which is very important to increase the resilience of very large workflows. Moreover, workflow documents can also contribute to FAIR principle, which is now becoming key in the scientific process, as this can be coded into a single self-contained and in most cases also portable document, which describes the analysis to be performed. And this can be used also by other scientists in a, let's say, reproducible fashion. So this is also a very important aspect. So Ophidia provides support for workflows, as introduced yesterday. The HPDA framework tries to support data-intensive analysis on multidimensional data by joining aspects from HPC and big data. And the server-side approach implemented in the framework allows executing tasks on the computing infrastructure, and this targets also the execution of workflows. In fact, the platform provides a workflow management system to support the execution of complex experiments composed of several hundreds of data analytic tasks, which can be applied on data groups and on input data. And is also able to interact with the HPC infrastructure for the proper execution of these tasks. In this slide, we can see some examples of workflows which have been defined and executed with the Ophidia framework. Some are more complex than others. Like, for example, there are a lot of different branches or a lot of tasks which are being run. I'm not sure how familiar you are with the workflow concept, but to put it in simple terms, it could be thought as a set of steps which are called tasks, which can be carried out sequentially based on a particular order, which is identified according to the tasks and dependencies. So workflow structure can be a simple sequence of tasks, which is the simplest workflow as possible, but it can also be more complex structure, like, for example, trees and graphs of tasks, in which the task can be connected to other different tasks. And so this can allow the execution of a very complex analysis where multiple tasks can produce the input for the following task and so on. So in this figure that we see here, the circles represent the task while the lines represent the dependencies. So the typical order is that the first task to be executed are those which are on the upper part of the figure, while those which are the dependent ones will be following. In Ophidia, we have defined a JSON schema for the workflow representation. And so this JSON format has been preferred to other formats like XML, since it has a lower overhead, but still it doesn't impose any strict schema for the file structure. So it's very easy and flexible to define a workflow structure. The Ophidia Workflow Manager is able to manage complex workflows in the form of direct acyclic graphs of tasks, which are basically directed graphs, which mean graphs with direct edges that don't have any cycle. In this case, we can then think of as tasks being the nodes of these graphs, while the dependency can be represented as the edges. The workflow system supports different type of constructs, and we will see this later in the next slide. So, as mentioned yesterday, this slide represents the high-level diagram of the Ophidia architecture. And in particular, today we'll focus on the top layer, which is the Ophidia server, which is, as said, the front end of the system, and it also hosts the workflow management system, which is part of the server. So the server, in this respect, manages the scheduling, submission, and monitoring of various tasks. And this task management has been implemented to be very flexible and extendable so that it can interact with different types of HPC scheduler, like LSF and SLARM, which are two of the most common. And the various clients which have been implemented, like for example, the Ophidia terminal, the PyOphidia module, also WPS clients, can be used from the client side to initiate the execution of the workflows, and then run interaction with the server, which will take care of the actual execution of these data analytics operations. Here we can see the Ophidia terminal, which we already introduced yesterday, but we'll go more in detail today. So this resembles a bash command line interface and provides many of the features of a traditional Linux shell, including, for example, auto-completion or command history management, environment and variable definition. Those also support for command aliases, variable substitution. But it's been implemented with respect to classical shells for executing specifically the Ophidia operators and the workflow. So it's tailored to the specific platform. The terminal takes care of translating the user commands, which are shown, for example, in this figure. This OPH list is a particular Ophidia operator, and then translate this command into the proper request and submit this to the Ophidia server, which in turn will take care of executing this on the computing infrastructure. The terminal can be very useful in different cases, for example, for executing fast and interactive testing of data analysis commands, so to see if everything works as we expect. Or for example, for debugging the environment and the operators to explore the file system. But it's also very useful in the case of workflows, since it provides the features to monitor the whole workflow execution. And we will see this in one of the next slides. So I said the workflow management system is part of the Ophidia server, is the key component responsible for managing the workflow execution. Here we can see an in-depth view of the Ophidia server internals and the main components which are related to the workflow management, which are shown in the central part of this diagram. So the workflow management system takes care of parsing and validating the workflow requests. It substitutes the parameters at runtime, prepare the commands to be executed, and schedule the execution, actually their submission and execution on the resource managers. And this is done according to the dependencies specified in the JSON request. And of course, if there are tasks which are independent, the workflow management system is also able to schedule them concurrently so they can be run in parallel. The system takes also care of monitoring the job execution and keeping their status updated into the system catalog. So once the workflow is completed, it communicates the results of the execution to the client side. And this will consist basically in a list of tasks and their execution status, let's say. Of course, the workflow management system takes also care of handling the advanced constructs which are defined into the JSON request. So now go more into the details of the JSON representation used in the Ophidia framework and some of the main features which are supported for building workflows. So here we can see the main supported abstraction for the workflow schema. So basically, the schema defines all the semantics and syntactic rules to be followed in the workflow documents. And so the main support abstraction include shared properties, data and flow dependencies, also simple task definition, as well as parallel groups of tasks, flow and error control, and also interleaving and interactive tasks, which allow to delay the workflow execution based on some input signal or external conditions. As said, the workflow is implemented according to this JSON schema, and is able to support the computation as the direct acyclic graphs. Here we can see how a workflow in a JSON schema looks like. So this is a snippet of a video workflow in this JSON format. And so here there are different tasks which are defined by these blocks in this parentheses. And for each one, we can define the name of the task, which will be used for the dependencies, the operator name, for example, we saw this also in the previous sessions, and then the list of arguments for that particular operator. In this case, we are running a loop operation, and this in red represents the two loops that we are starting with. These are nested, one inside the other, and then we have in these white blocks, this white rectangle, which highlight the different tasks composing this workflow. On the right part of the slide, we can see the translation of this workflow from the JSON to the graph representation, where the circle represents a different task, and this hexagon shape represents the particular flow control structure, in this case, the loop tasks. So as said, the tasks are executed based on dependencies, which are the lines in the graph in yellow, as we can see here. These are specified by linking each task to the name of the one it depends on. Like, for example, in this case, we have a dependency on compute operation over time, which is the previous task. Of course, dependency can also be defined on multiple tasks. So, for example, there could be tasks which depend on 2 or 3 other tasks. So they cannot start before these 2 or 3 other tasks have been executed. So dependency define the order in which tasks are submitted by the workflow management system, which, as said, takes care of tracking the execution status and understand when the other task can be submitted. So tasks can be in different states, like, for example, pending, running, or completed. And these are associated with different colors, as you can see in this slide. To ease the monitoring of large workflows from a user point of view, the Ophidia terminal provides also a graphical representation of the workflow execution, which are this graph structure that we can see here. In this slide, a very simple example of a workflow composed of 3 tasks, and the various stages in which these tasks can be is represented. So we can see that before starting the execution, all the tasks are represented in white, and this is sort of a static workflow representation, which shows the different tasks within the workflow. Then once this is submitted, the first 2 tasks are executed, so they go in a running state, and there are thus represented by these orange colors. And then the third task waits until its dependencies are completed, so it is colored in gray because it is in a waiting state. Tasks can be completed successfully, and in this case are colored in green, or they can fail and are represented in red color. If one of the first 2 tasks fails, the workflow can stop or proceed on running the following task based on the user specification. And we will see how the workflow manager is capable of handling task failures in different ways according to some rules that can be specified in the JSON file. If all dependencies are executed successfully, then the third task will be executed, and then we'll turn in this orange, which is the running state. And at the end, when all the tasks will be completely executed and successfully executed, all the tasks are represented as completed, and thus in this green color. Now I would like to show how our workflow is submitted from the Ophidia terminal. Workflow can also be submitted from the Ophidia module, and Fabrizio will show some examples later in the practical part. So in the first line of the terminal, we can basically specify the JSON file. In this case, it's called t_end_loop. And then this is followed by a set of arguments that we replace at runtime within the workflow. So we're specifying 2 data cubes and max, which is an argument associated to the type of data reduction to be computed. Once this is submitted, the server will return a job by identifier, which is this very long string here, which includes information about the session and the particular server contacted, but we're interested mainly in this final number here, which represents the workflow identifier, particularly in this case, this 247. So the workflow identifier can be used to monitor the workflow execution progress. So if we run this view command from the terminal, we can then see this summary of the execution of the workflow. And this is presented in a tabular format to ease the understanding. So here we see that in this yellow part, that 82 tasks have been executed and 82 of them have been completed. And this is because the workflow status is basically completed. It means that all the tasks have been successfully executed. Whereas in the second table below, we can see more detail on each of the tasks composing the workflow. In particular, we have the task name, which was the name we defined in the JSON file, and the status of each task. In this case, I were completed, but there could also be tasks which are failed with error or maybe skipped because they were in paths that were not executed by the workflow. The terminal, as I said, is also able to monitor graphically the workflow execution. This is done by setting a specific option in the terminal. If this option is enabled, then this image will just pop out showing the different states as this was defined in the previous slide. And the output which is shown here is not the actual output of the workflow at this state, because the workflow was completely executed, but this is just for showing how it would look like during its execution. So here we have some tasks which are already completed and other which are running, and then other are still waiting to be executed based on their dependencies. So, okay, I said the workflow management system support different features to implement complex workflows. So, for example, it supports different types of dependencies, error control operation, loops of blocks of tasks, like, for example, sort of a iteration structure, but also parallel independent branch that can be run concurrently, as well as conditional workflows with if-else structure. Here we can see this is just a subset of the operation available. This has been taken from the Ophidia documentation. So we can now go more into the details of these different abstractions which are made available. So the first one is the Iterative Interface, which allows a user to define loops of tasks which are run in basically a set of sequential iterations of tasks which are based on certain condition. And this condition can be embedded into the workflow or provided also as argument at runtime in order to define, for example, the number of loops in this loop interface every time the workflow is submitted. So the snippet in the lower part of the slide, which representative shows an example of the loop where the counter basically represents the number of iterations. In this case, there are 12. The loop abstraction can be used to repeat the execution of a block of tasks over different data, or, for example, useful in the case the results of an iteration depends on the previous one. The OPH4 and OPHN4 operators are used to define the blocks of tasks that have to be run for each iteration. Of course, the task within an iteration can still be run concurrently according on their dependency. So if they're independent, they can be run in parallel within the same branch, but then the different iterations are run in a sequential way. The for interface can also be used in a nested way, so that we can basically nest a workflow within another workflow, and this supports the execution of loops within loops. The figure here on the right part of the slide, we can see there are two figures. The first one with all the white task is basically the static definition of the workflow graph, whereas on the right part we can see this runtime view of the same graph. So additional info can be found on the documentation if you're more interested about this particular functionality. The loop abstraction supports also an extension to run the various branches concurrently, and this is very useful when there is no dependency among the iterations. In this case, as shown in the snippet, we can simply enable this by specifying this argument parallel equal yes. And the workflow management system will then transform the simple compact version of the workflow, you can see the definition time here, into the one that we see in the lower part of the slide, where this is basically expanded into this 12 task, and this can all be run concurrently. So this is a very useful option to parallelize the execution in all those cases in which basically the different branches can be run concurrently on different input data or on different data tubes. Ophidia workflow can also model conditional execution of task, which is similar to an if-else traditional coding, let's say. So this selection interface allows to define different paths of task, which can be selected dynamically when the workflow is executed, and this is based on some Boolean expressions which are provided as condition to the select interface. And this can be specified as for the iterative interface, both in the workflow statically, but also as argument of the workflow at submission time. The system provides 4 different interfaces for this. So this is the if, else, and else if, and if operators, and this can be used to build even complex and also nested conditional execution. So this allows, for example, to select one branch of the workflow instead of the other, and this can also be done with multiple conditions. So according to the input arguments, and also this can the condition can also be evaluated also by taking as input the output of a previous task, for example. Here we see the example again of the statical graph view, and the one which is executed at runtime. In this case, the else branch is executed, whereas the if one is just skipped. So this task will not be executed. So as I mentioned earlier, a very useful feature to handle workflow execution, especially when these workflows are very large and complex, is the possibility to handle task failure. And this is important to increase the workflow resiliency, especially in the case of workflows which are composed of many tasks. So just this can allow to stop the whole workflow execution if just one single task fails. So Ophidia supports multiple behaviors, and we can see the different arguments which are defined. And this allows to, let's say, to take different action in case of failures to a task applies. The default behavior is to interrupt the whole workflow, and this is this break argument, which is shown here. But then there are also different arguments which allow just to simply ignore a task, the task which is failing, and continue with the other one. Or also there's the possibility to resubmit the task again before interrupting this workflow. So the task could be executed a certain number of times before stopping it, just to be sure. For example, if there is like some files are not available, so this task could be re-executed to see if maybe after some time this data becomes then available. Here we can see a couple of snippets of the use of this error handling feature. So in the upper snippet, here we can see that this is defined at the global workflow level. So it means that this on error, which means how to handle the task failure, will be applied to all the tasks of the workflow. Whereas this can also be applied at the level of a single task. So here we can specify, for example, for this operator PHP, we use the one to repeat this n times. And of course, if we define both the global and task level error handling feature, the one at task level will have precedence with respect to the one at the global level. So here we can see basically the output of some workflows that we implemented with the Ophidia framework by using the interfaces that we just specified. These are being produced with different tools like Python libraries or Panoply tools, and represent some real use cases that were implemented with the workflow features. So I would like to show some of these real-world analytic use cases that we implemented with Ophidia as workflows. So the first one is this workflow implemented in the scope of the Eclipse project some years ago. And in this case, a single workflow was defined to model 3 different indicators, all within a single analysis document. So basically, this included a monthly average, the anomaly of the monthly average, and the climatological monthly average. And this was applied on a large data set from ESA, SST, the Sea Surface Temperature Climate Change Initiative, and consisted of more than 7,000 files, about 340 gigabytes, with a very high global spatial resolution. The workflow in this case consisted of about 87 tasks and produced different output. The lower part of the slide shows just one of the maps produced on these netcdf output files. And here on the right side, we can see the graph showing the workflow execution. And in this case, the workflow approach was very useful because it allowed to automate the parallel execution of various tasks without needing to implement all this manually, basically. In this slide, we see a second example, again from the Eclipse project. Also, in this case, the indicators were computed within a single workflow. And in this case, these are the basically the first snow day of the season, the last snow day of the season, and the length of the snow season. And this is based on the ESA Globe Snow dataset covering 30 years and consisting of more than 6,000 files, about 15 gigabytes. So although the file size in this case is not very big, the workflow consisted of around 600 tasks. So of course, managing this manually would have been very difficult. And instead, in the workflow definition in JSON, it was composed about just 20 tasks. And then when executing this on the workflow manager, these are translated to 600 tasks, as we can see in the graph produced by the terminal. And this was done thanks to the parallel loop interface that was presented a couple of slides ago, which allows to run concurrently the different branches composing this workflow. So in this case, the workflow approach allowed to handle in parallel a very large number of tasks with a very simple workflow description. And so this proved to be very useful. As a third example, we implemented also a multi-model climate analysis as an Ophidia workflow. And this example shows the precipitation trend analysis. The diagram represents just a graphical high-level view of the workflow. In this case, the circle represents the Ophidia operators, while the lines are the dependencies. This is just a logical view, let's say a high-level view of the workflow, highlighting the main operators. The actual workflow is still written in JSON format and contains also some auxiliary tasks which are not inserted here, just to have those which are more important. So the experiment is composed by two parts. In the first stage, we can see that multiple identical sub-workflows are executed to compute the trend analysis of the data of different models. So every blue box represents the analysis on a different model. And for each of these sub-workflows, two identical branches are defined to extract the precipitation trend from an historical and a future SMIP dataset. For example, the RCP 8.5 from the SMIP5 dataset. And then at the end of these two branches are compared to get a difference in the trend from the two periods. The second stage then is applied to all the results of the first stage. And this basically tries to compute some statistical values over the precipitation trend analysis of each single model. And then it produces as output some maps and some CDF data. The workflow has been executed with multiple SMIP datasets. In particular, in this SMIP5 implementation was applied on 18 different models for a total of 150 gigabytes. And the workflow is able to easily scale with a number of models involved, again, by using the parallel loop abstraction. So also in this case, we can basically scale this on the number of models involved. The number of tasks defined in the JSON document to implement this particular workflow, which is here we can see a snippet of this JSON is around 30 tasks. But then this at runtime is translated by the workflow manager in almost 300 tasks. And here we can see the graph which is produced by running this workflow on the Ophidia platform. And we can see also the different stages of the workflow. So this first part with multiple parallel branches represents the first stage of the workflow, whereas this second part here merge together the results of the different branches and perform the statistical analysis on the ensemble of data. And here we can see the final maps which have been created with Cartopy based on the statistical analysis performed. As final point for this workflow example, which is interesting, we try to implement the same multimodal analysis also with Ophidia module as a Python notebook. The main difference is that in the Python case, the user must take care of handling the parallel execution on the independent task. Whereas with the workflow, this is automatically managed by the workflow management system based on the dependency defined in the JSON format. So even after some optimization to the Python code in order to enable parallel execution, the workflow version is still faster. And so this shows the importance of this workflow approach when, especially when managing large-scale analysis where hundreds of tasks have to be executed. And so in this case, if managing this task execution manually, it could be very daunting. So the workflow system can instead support the user by relieving the user from thinking of how to parallelize all the analysis execution, and also from performing this meticulous optimization on the code. Before concluding, a quick summary of this first part of the session. So we saw how workflows can effectively support the implementation and execution of complex and large-scale climate analysis. Ophidia provides different features and interfaces to handle very complex workflow of hundreds of tasks. And we also saw some real-world examples. As the next part of this session, we focus more on practical aspects, and Fabrizio will show how to build and execute workflows of Ophidia operators. And then also here I've just placed some references to related work also concerning Ophidia, what was presented today. And there are also some links as yesterday. And thanks to the Easy Ways project for supporting these training activities.